tweak the way AI picks and learns with losses mixed in clever turns. Logistic, exponential, watch them blend. Auto-discovered, not just pinned. Today, we're diving into an interesting paper that Sakana AI researchers just discussed on Machine Learning Street Talk. Can AI improve itself? Instead of manually designing how models learn, they let an LLM generate and test its own loss functions. No human in the loop. So how does it work? Let's dive in.
LLMs start out as very general learners, thanks to massive pre-training on text. But to ensure they align with human preferences so they don't produce harmful or misleading content, we typically fine-tune them. The usual method for this is reinforcement learning with human feedback, or RLHF. How does it work? We collect outputs from the model, ask humans to rank them, train a separate model to mimic those rankings, and then run a reinforcement learning loop that pushes the main LLM to produce better outputs. Recently, a simpler method called offline preference optimization has gained traction. It ditches reinforcement learning and treats the problem more like supervised learning. The crux is designing the right loss function, the mathematical rule that tells the model how to adjust during training based on human preferences. So far, experts have handcrafted these loss functions. But human intuition has limits. There's a much larger space of possibilities out there. This paper proposes a new approach. Prompt an LLM to generate candidate loss functions, evaluate them, and refine them iteratively, effectively automating the discovery of optimization rules. The most promising function they uncover is called DiscoPOP, which is a mix of logistic and exponential loss components. We'll see soon that it outperforms existing methods on multiple tasks. Ready to see how they do it? Let's move on. This next section dives deeper into how they get LLMs to design their own optimization rules. Picture this. You prompt an LLM with examples of existing loss functions and some performance data. The LLM then invents new loss functions, which get tested in real trainings. The results come back, and the LLM uses that feedback to revise its proposals. It's an iterative loop, a bit like a conversation, where the LLM keeps improving its ideas. Here's a key takeaway. One of the new functions discovered is DiscoPOP, blending both logistic and exponential terms. If you check out something like Alpaca Eval here, you'll see that DiscoPOP consistently outperforms other methods. There's even a neat figure showing how it stacks up in a head-to-head comparison against GPT-4-tuned models. And DiscoPOP leads in many scenarios. But why is preference optimization so critical? Well, LLMs are aligned with human values or preferences through a reward signal, either via RLHF or some direct loss-based method. This paper suggests that instead of refining your reward model, you might do better by discovering totally new loss functions that do the alignment more effectively. Let's see how they do that in practice. Typically, fine-tuning an LLM goes like this. You train a separate reward model to score responses. Then you use reinforcement learning to make your main model generate outputs that score high. This is complex, it's computationally heavy, and it can be unstable. The alternative? Direct preference optimization. Instead of training a reward model, you directly train the LLM to produce preferred responses. Doing that requires a loss function that captures how well an answer matches a human's preference ranking. Think of it like a classifier deciding which of two answers is better. Different loss functions can nudge the model towards smaller, safer updates, or allow big changes when it's sure one answer is superior. The paper's main thrust is to have the LLM itself figure out the best possible loss function. This meta-optimization approach means the LLM proposes a function, sees how it performs, and iterates until it finds a strong candidate, removing the need for humans to guess formulas. Let's see how that iteration works in more detail. Here's where we see the heart of the automated discovery loop. The LLM is given examples of existing loss functions and their performance results. It generates brand new loss functions, complete with Python code, and runs them through unit tests to ensure they make sense. After that, these functions get evaluated on a task like image classification, and performance metrics flow back to the LLM. The model updates its strategy based on this feedback, repeating the cycle until it arrives at a set of promising candidates. Want a concrete example? Look at how they used CIFAR-10, a classic image classification dataset. At first, the LLM suggests small tweaks to cross-entropy. Later, it experiments with squared error variance, and eventually, it combines insights from different attempts. Each generation of discovered functions builds on what worked in previous generations. By the end, the LLM has developed loss functions that generalize well to different architectures, indicating it's learning principles rather than overfitting to one dataset. Isn't that neat? It's not just random searching. It's cumulative learning. This sets the stage for using the same approach in other domains, like dialogue or summarization. So how does it fare on more human-centric tasks, like multi-turn dialogue evaluation? That's what they explore next. The method is the same. The LLM proposes a bunch of preference optimization loss functions. The functions are tested in training, and the best ones are refined. They measure results using a benchmark called MT-bench, which checks how natural and helpful the dialogue responses are. If you look at the line plots here, you'll see how performance trends upward across these iterative discoveries. The model is basically learning from each generation's outcomes. In these experiments, they highlight a newly found function dubbed log ratio modulated loss, or LRML. LRML, which they also call DiscoPOP in some sections, combines elements from earlier ideas and ends up performing quite well on MT-bench. That's a strong indication that auto-discovering loss functions can yield better conversation alignment than many tried-and-true methods. See if this holds for even more tasks. Next up, they validate these freshly discovered functions on real tasks like dialogue generation and summarization. One key benchmark is Alpaca Eval 2.0, where you compare how well an LLM's answers align with human preferences, side by side with GPT-4. The table in front of you shows that the newly discovered loss functions, particularly PADLL, AQFL, and DiscoPOP, outperform several established methods. This suggests that these automated discoveries aren't just quirky new experiments. They really work. They also test summarization using the TLDR dataset from Reddit, where the goal is to produce concise summaries of posts. Again, they drop in their discovered loss functions instead of a standard approach, and they measure performance. The results confirm that these new functions seem broadly applicable. They're not just overfitting to a single domain. The paper emphasizes that strong results on two very different tasks, dialogue and summarization, show real promise. Here the focus is on diving deeper into the summarization results with the TLDR dataset. You might see a table showing that performance adaptive decay loss, or PADLL, and direct preference optimization, or DPO, often top the leaderboard, although DiscoPOP, the same as LRML, can beat them in certain submetrics. This variation suggests that the best loss function might depend on the specifics of the task. They then switch over to sentiment control using IMDb movie reviews. The model has to generate text that matches a particular sentiment. Different loss functions, different performance. In some setups, DiscoPOP maintains a higher reward, especially at lower regularization. The takeaway is that each function has its sweet spot. Finally, there's a deeper analysis of DiscoPOP. It dynamically balances logistic and exponential terms. If the model's off track by a large margin, the exponential part kicks in harder. If it's already close, the logistic component dominates for finer-grained tuning. This adaptive blend can help avoid plateaus or pitfalls in training. Curious how DiscoPOP, or LRML, really works under the hood? This section shows you. It actively shifts weight between two terms, a logistic loss and an exponential loss. Early in training, both are balanced about equally, especially if the model's outputs don't deviate much from a reference. But if the model really veers off course, that exponential term ramps up and yanks it back on track. Take a peek at figure 5 here. On the left, you'll see how LRML compares with popular approaches like DPO or SLIC, balancing strong rewards without massive divergence from a baseline. On the right, you'll see the same comparison extended to more loss functions. DiscoPOP's adaptability is on display across these setups. Then there's figure 6, where they show how DiscoPOP can introduce a non-convex region in its optimization. That might sound risky, but it can also help the model escape local minima. One caveat. The paper notices that extreme settings of the parameter beta can cause convergence issues. Why? Because the discovered function didn't get exposed to extreme beta values during its own childhood, so to speak. If we want it to handle exotic settings, we probably need more diverse training scenarios. Finally, let's place this in a broader context. People have been using LLMs for all sorts of algorithm design tasks, neural architecture search, code generation, robotics control strategies, you name it. The main pattern is similar. Feed examples and results into an LLM, get new designs, evaluate them, loop. Some folks use genetic algorithms, others do reinforcement learning for meta-optimization. The big picture is the same. We're letting AI propose solutions, and then we refine or filter them. In conclusion, this paper shows that an LLM-driven approach can discover loss functions, like DiscoPOP, that surpass human-designed methods on multiple tasks. They note that mixing logistic and exponential components, plus some non-convex behavior, could be key for robust preference optimization. Still, it's early days. They tried adjusting the LLM's search parameters a bit and didn't see dramatic gains. Future directions might include more sophisticated ways to guide the LLM's search, perhaps by incorporating visual learning curves or advanced meta-learning strategies. Thanks for joining us today. Happy exploring!